Here in section 8.2, we're going to explore another geometric concept with finding the area of a surface of revolution. A surface of revolution is a surface that's formed by revolving a curve about an axis. So imagine I take a curve y equals f of x, and then I form a surface by revolving this curve, say for instance about the x-axis. And that's going to form this three-dimensional surface, and our goal now is to try and find the area of this surface that's formed when we revolve f of x around an axis. Before we get to the formula, we'll need to develop a little bit of some basic geometric facts. First, if I have a cylinder, we know that if I slice a cylinder and unravel it, it just forms a rectangle. So the surface area of a cylinder is 2 pi times 2 pi r, which gives me the base of one side of the rectangle, times h, which is the height of the cylinder. So 2 pi r being the circumference of the base of our cylinder times the height gives us the surface area of the cylinder. Similarly, if I take a cone and I slice that cone from the tip down to a point on the edge of the cone and unravel it, we get a sector of a circle. So we can then find the area of our cone using our knowledge about finding the area of a sector of a circle. So to remind you, the area of a sector is going to be 1/2 r squared theta, where theta is the central angle. Notice that the radius of this sector is not actually r. R is the radius of our cone. When we unravel this surface, the radius of the sector is actually L. So it'll be 1/2 L squared theta. Now to get theta in terms of r, we're going to use how this angle, the central angle theta, relates to the arc of the circle here. So the arc of the circle will equal to the radius of the circle times the central angle. In this case, the radius is L and the central angle is theta. So it should equal to L theta. And so therefore theta can be written as 2 pi r over L. So replacing theta here with that, you notice here some things simplify. The 2's divide and one of these L's divide, leaving me with just pi RL. L being the slant height of our cone, R being the radius of our cone. So that gives us the surface area of that cone. Now let's consider slicing our cone at some point, which creates a band. To find the area of the band, we'll take the area of the bigger cone and subtract the area of the smaller cone at the top. So the bigger cone, of course, would be the entire thing, and then I'm slicing off the top cone there, so we'll call that the smaller cone. So the bigger cone has a radius of r2, so it'll be pi times r2, and then the slant height would be L1 plus L. And then the smaller cone that we're subtracting off the top has a radius of r1 and a slant height of L1, so we're going to subtract pi times r1 L1. So just a little bit of rewriting this here if I expand it out a little bit. one thing we can try and do now is relate L1 with L somehow, and the way we can do that is we can use similar triangles. Because we notice that here this smaller triangle with a one side is R1 and then the hypotenuse side would be L1. So the ratio R1 over L1 should equal to the ratio of the bigger triangle R2 to its hypotenuse, which would be L plus L1. So R2 over L plus L1. If I cross multiply here, I have R1 times L plus L1 equals R2 times L1. Distributing it out, I have R1L plus R1L1 equals R2L1. And what I notice now is if I bring these two terms that have L1 onto one side, I see something similar over here. I have R2L1 minus R1L1. In fact, if I group those together, I notice that I can replace that with just R1L. And so here we see it's really just pi times R1 plus R2 times the slant height L, which is, L is actually the difference between the large slant height and the small slant height. So it's just, L is just this length of the segment that goes from one end of the band to the other. And if we just do a little replacement with what we're calling R will be the average between R1 and R2. So you add them and divide by 2. So therefore R1 plus R2 will equal to 2 times R. So therefore here we get the area of our band will be pi times 2R times L. So I'll write 2 pi RL. That gives us now the formula for the area of our band. And why is this important? Well, this is essentially how we're going to form our surface area, is by using these approximating bands. So now if we imagine back to our curve that's going to be revolved around the x-axis. If we partition the interval from A to B into subintervals like we would normally do if, for instance, we were finding the surface area, that's the arc length, that's exactly what we did. So now that we're finding the surface area, we're going to take each of these segments that form on that we form on the outside, so that when we revolve it around, it's going to form an approximating band. And we know the area of this band, say this first band here, call it A1, will have an area of 2 pi r, which will now be a radius of some value in the middle, in between. R1 would be f of x0 and R2 would be f of x1, so some function value in between. So we'll do 2 pi times f of x1 star. And the length of that segment there will be, if this is P0 and P1, it'll be the length of that segment P0, P1. Which, as we recall when we did surface area, this can essentially be approximated with the square root of 1 plus f prime of xi star squared times delta x. So we see now that this is going to be approximating here. Actually, I put A1, but this could be true for any of those approximating bands. So I'll call it AI. So instead of P0 to P1, you could do from Pi minus 1 to Pi, and this would be Xi star. So that would be just one random approximating band, so then we can sum them up over this interval from A to B. Okay, so here again we can kind of see our approximating band. And so the surface area of the whole thing, we'll call S, will be the limit as n goes to infinity of the sum of these approximating bands, which will have what we mentioned in the previous slide, an area of 2 pi f of xi star times the square root of 1 plus f prime of xi star squared times delta x. And then we know that summing this up and taking the limit as n goes to infinity will be a Riemann sum that approaches the integral from a to b of 2 pi f of x square root of 1 plus f prime of x squared dx. And what you may notice is actually this is the arc length differential here that we discussed in the previous section, ds. So when we're looking at the arc length formula here, so this gives the area of the surface formed by revolving the curve y equals f of x about the x-axis. Right? We mentioned that this is just the arc length differential ds, and then this is like the y-coordinate of our curve. So one kind of shorthand way that we can think of this is the surface area is the integral of 2 pi y ds. We'll see why this is actually a nice simple way to condense the formula a little bit in a way that's easier to remember. And in a way it kind of gives us a good geometric way to think about it. Because here we can imagine that if we're finding the area of the surface from revolving it around the x-axis, we're essentially summing up a bunch of rings. We can imagine that the ring would be the outer circumference of this circle, where the radius of that circle is the y-coordinate. So the circumference of that circle would be 2 pi times the radius, or 2 pi y. And so we're going to be summing up with the integral 2 pi y times the arc length ds. So in a similar way, if I were to revolve around the y-axis, we can do a similar argument that now we're going to be finding the circumference of a circle that is formed in a different way, where now the radius of that circle is x, and so its circumference would be 2 pi x. And so then we're summing up all these circumferences from one end to the next on this surface. And so doing that would give us this arc length integral, the integral of 2 pi x ds. Okay? And again, this is nice in general because now, regardless of whether we're integrating with respect to x or with respect to y, ds can represent either case. So ds could represent here when you're given y as a function of x, right? Or it could represent this case here where you have x as a function of y. So this would be in the case when you wanted to integrate with respect to the y variable, and this would be the case when you wanted to integrate with respect to the x variable. So you can interchange between these two different forms, and you don't have to do a different formula. It's all kind of contained in this one formula here. And let's just do an example to demonstrate it. In this example, we have the curve y equals the square root of 4 minus x squared from -1 to 1. So it's like this little piece of a circle of radius 2, and then we're going to revolve it around the x-axis to form this surface. So here's a picture of what we're going to try and find the surface area of. So we know it'll be the integral of 2 pi y ds, just to remember that nice shorthand form of the formula. So let's now fill in the details. We're integrating from -1 to 1, 2 pi y. Now the function that we're integrating for y is square root of 4 minus x squared. And then the square root of 1 plus y prime squared. So we need to fill that in here. So let's find y prime. So think of this as like 4 minus x squared to the 1/2 power. So we're going to do 1/2, 4 minus x squared to the -1/2 power, times the derivative of 4 minus x squared, which will be negative 2x. And I can simplify this a little bit. For instance, here the 2's divide. And then I can bring the -1/2 power to the bottom. So this will be negative x over the square root of 4 minus x squared. Okay, so now we can insert that in our formula here. Okay, well let's see if we can simplify this a little bit. Take the 2 pi out from the integral. When I square my derivative here, I get x squared over 4 minus x squared without the square root. Okay. Next thing I can do is actually combine these two terms here to get a single fraction. Okay, so doing that we get 4 minus x squared over 4 minus x squared plus x squared over 4 minus x squared. Notice then x squared minus x squared, we're just left with 4 when we combine them. Okay. Notice here, actually, we can do a little bit more to simplify it. Since we got the 4 minus x squared and the square root of 4 minus x squared here in the bottom, we can cancel those. Because essentially, I can split up the square root here. So you got square root of 4 on the top is 2, and then you got the square root of 4 minus x squared here in the bottom, and now those square roots will divide. And now my integral is just the constant 2. So that's a very easy integral to evaluate now. It'll just be 2x evaluated from -1 to 1. Okay, so now we have 4 pi, 1 minus -1, so that'll be 8 pi.